very important for understanding this transformation. And the next was the problem of nucleation of tetragonal zirconia, the monoclinic zirconia during the transformation. This problem was discussed, taking into consideration true materials concerning zirconia. I mean tetragonal zirconia polycrystals and partially stabilized zirconias, and the role of particle size. Huge knowledge, I think. But can we start from the problem of ceramic powder agglomeration? Could somebody explain what is the driving force? Sorry? Okay, you can. TM means just a moment, because TM, Tomkiewicz Marcin, yes? Am I right? No? Who wants? Okay, Marceli. Okay. Yes. Mm-hmm. Yes. What is the driving force, and what is the mechanism of agglomeration? Simply for coarse grain. But the reason is, Okay, but this is okay, but it is the reason when we take into consideration thermodynamics of the system, but the movement is caused by the action of forces. Uh, yes, and we observe the result. But you said that okay, you said that for large particles, the gravitational force and the forces that act in the contacts between particles, that there is a balance uh, between those two forces. Is that true? I I think that there is only one case in which those forces should be in balance. I mean that the gravitational force which comes from the mass of a sample is equal to the, for example, the accesive or cohesive forces between particles. Only one. But when masses are larger or lower, when compared to this uh, mentioned by me earlier, there is no balance because, but as I said, but this is thermodynamics. But please tell me about forces. They agglomerate because what is the relationship between the relation, simple relation between the gravitational force and the forces that act in the contact between. Yes, that's right. Thank you very much. I think it's clear for everybody that agglomeration process is caused by from the thermodynamic point of view is caused by the excess of surface free energy. But when we take into consideration the forces that act, it means that the process of agglomeration appears when the weight of particles is very small, and the contacts is and the contact is, let me say, strong enough to withstand the action of gravity. Yes. Okay. And next problem, I don't know Is it easy or no for you? But it is interesting for me. What is the topic for? XRD and BET methods used to determine the state of agglomeration of ceramic powders. How do you understand this topic? Is it possible to take any information about the state of agglomeration of powder when we collect the data coming from XRD measurement and from the BET measurement. BET means the measurement of a specific surface area of the powder. Who wants to start the discussion? Mr. Polacek Artur is present?
Yes, I am, but I don't feel too good with this topic. I don't remember really.
Okay, maybe you remember. Remember what information, what characteristic of the powder can be taken from the X-ray diffraction measurement. Do you remember? What we can measure with respect to the characteristics of the powder by using this method?
Chemical composition?
Yes, it's possible, but it's not this characteristic which can be comparable with the characteristics obtained by the BET method. BET method measures this specific surface area. Do you know the definition of the specific surface area?
Yes, I think so. It is the area per volume.
Yes, no volume. The area per mass.
Per mass, okay.
Per mass, yes, per mass. And strictly when the specific surface area, when the specific surface area of the powder is large, let me say, what is your expectation about the powder when you compare with the lower values of specific surface area for the same powder?
Well, the powder with bigger specific surface area will tend to agglomerate more.
You suggest that we can obtain directly this information from the specific surface area measurement.
I believe so.
Okay. It is not true, because not directly. We must compare. What information is taken directly from the specific surface area measurement?
Do you mean the average size of grain?
Yes, the equivalent particle size. Equivalent particle size.
Mm.
Is it possible to determine any size of particle by using X-ray diffraction?
I'm not sure, but I would say yes.
Yes, you are right. But the idea, I think you don't know of this measurement.
No, I only recall using this method to calculate, for example, the size of the unit inside the structure, but not in the macro scale. Sorry. I don't remember the principle behind measuring the macro scale of powder.
Maybe you remember that when we consider the X-ray line broadening, it is possible to determine the size of crystallites, the size of particles.
Okay, maybe it rings a bell.
That's true. Okay. Okay. Mr. Talowski, Patrick, could you continue?
I think so, maybe.
Because do you know and do you know the idea of the measurement, the determination of crystallite size by using X-ray diffraction method, X-ray light broadening? The X-ray light broadening is considered.
I mean, the diffraction of the different crystal sites in the spectrum, is that it?
Okay.
The different sizes, grains diffract differently in the spectrum. Is that it, or am I completely in a different field here?
It's a difficult problem for you, I think. Okay. Let me go to, I think, more easier problem. Polymorphism of zirconium oxide. Polymorphism of zirconium oxide. Mr. Patrick Talowski, could you begin description of the polymorphism of zirconium dioxide?
The zirconium oxide exists mainly in three different polymorphs. It's monoclinic, tetragonal, and cubic structure. And the phase transition happen with the increase in temperature. It starts at the in the monoclinic, and as the temperature goes up, it goes into tetragonal and cubic. Between the monoclinic and tetragonal, there's a density spike and a specific volume spike, so that's the reason the material is used widely in ceramics as a phase transition material. More about that, or go in deeper?
Yes. Okay.
What else?
Okay. In your opinion, the transformations, polymorphic transformations between cubic and tetragonal phase, and the transformation between tetragonal and monoclinic, those transformations are the same in their nature?
They're not, because the monoclinic to tetragonal is much more valuable. It's a much bigger change in the structure of the material, and it's different because the transformation is martensic and the other one isn't.
Martensic, yes.
Martensic. So the change happens almost instantly and is diffusion. No, the other one is diffusionless too. The other changes, I mean, the volume and the density change is much bigger in the monoclinic to tetragonal than tetragonal to cubic. I don't know what more.
What more? Yes. The information which comes from this first slide, not screen, sorry. Okay. Wow. Just a moment. Just a moment. Why is the problem in? Wow. I wanted to show you the slide from my lecture, and I have a technical problem. I don't know why. Okay, just a moment. I try again. Whoa. Oh, screen, not screen. Just a moment. Oh, yes, it should be. Okay. Yes. Which one? I'm sorry. Please wait a while. I will solve the problem. AC. Not this one. Okay. Yes. Okay. I think you see the slide. Okay. 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 Whoa. This information is what feature of the Martinistic transformation is shown by this information?
That it's reversible at different temperature.
Yes, and the temperature is different for forward and back transformation. Yes.
Yes.
Okay, and why? Could you please explain us? Maybe.
Is it because of the stress that the transformation makes? I mean, when we lower the temperature, we have to make there's a volume change, so that we need more energy to create that volume. I don't know, maybe, or is it just the stress that the change entails?
Okay. Maybe you remember the magnetic transformation needs shear stress for appearing. Yes.
Yes.
Yes, and during cooling and during heating, we must generate appropriate shear stress, and we need to achieve appropriate thermodynamic driving force, simply, to generate the process which is barrierless, which is athermal. Okay, thank you very much, Mr. Patrick Talowski. Yes.
Yes.
Other structures, other polymorph of zirconia. Maybe Miss Sylvia Manteris wants to characterize.
Could you repeat the question?
Other structures, other polymers of zirconia I want to characterize.
So
monoclinic, tetragonal, and cubic.
So cubic form is a high temperature phase, and the oxygen are tetrahedral rotated themselves by 90-degree angle. So they create some kind of tetrahedral shape.
Yes, that's right. Yeah. Oxygen forms two tetrahedra in the cubic polymorph. Okay. The structure of the cubic zirconia is similar to or the same as the structure of other compound. Could you name it? Could you call it for us? Calcium fluoride. Yes. Yes, that's right. Calcium fluoride structure. Yes, good. And what is the coordination of zirconium ions in the structure in the cubic structure?
4+. I mean that they are on 4+. I don't know how to say it in English, to be honest.
The coordination of zirconia. Yes. Yes. Zirconia ions have 8-fold symmetry. 8-fold.
Okay, you mean that.
Coordination. Okay. Yes.
They creating zirconium 8, so they have to be 8-fold symmetry. Okay.
Okay. And oxygen ions are surrounded by 4 zirconia ions. Yes.
Yes.
Okay. Could you please tell us, what is this, the symmetry of this elementary cell? Is this cell body-centered or face-centered, in your opinion? Body-centered or face-centered symmetry?
I think that this is face-centered.
Face-centered. Yes, that's right. Okay, and what about tetragonal phase and monoclinic phase from the point of view of zirconia, zirconium ions coordination, and oxygen symmetry in the tetragonal phase?
So the oxygen is body facing and body shape is in the body conformation, and zirconia is in the face. I don't know if you mean exactly that, but I hope so.
Maybe you know what is the zirconium ion symmetry coordination in the monoclinic symmetry. In the cubic and the tetragonal one, the coordination is 8-fold. But what about monoclinic? The monoclinic phase.
Okay. So zirconium is 7-fold, I guess.
Yes, 7-fold coordination.
Yes.
Good.
And the oxygen.
Good.
And the oxygen is irregular in this form.
Sorry?
Oxygen is irregular in this form.
Wow. Okay. In this picture, you have the description of oxygen ions as 1 ABC and 2 ABCD. What does it mean? How do you imagine this? Let me say the arrangement of oxygen ions when we consider the planes which are occupied by oxygen ions.
To be honest, I don't know.
You don't know? Okay. What about this information? How do you understand it? The structure of oxygen not planar in the O2 coordination. The structure non-planar, buckling of the O2 plane exists, and the oxygen 1 plane quite irregular is in the structure.
That the two plane I don't know. Sorry.
You don't know. Simply you don't know. Simply, yes. And this is the solution of the problem. Yes. Okay. Is there? Okay, Miss Claudia Wyszczarz, in your opinion, is there any relation between this monoclinic structure and the tendency to the formation of the other structural forms that minimize the energy of the structure when the transformation of the tetragonal phase to monoclinic phase exists?
I'm not sure, but maybe the reason is that monoclinic phase is stable in low temperatures.
Yes, that's right. But okay, the transformation of the tetragonal grain to the monoclinic one appears. I think we can imagine this. And in your opinion, the whole tetragonal grain transforms into the monoclinic one, and this is, let me say, this is the main characteristic of this transformation. One grain one tetragonal grain transforms to one monoclinic grain with no additional, let me say, changes in the structure.
I don't think so, because as you can see, there are also like a backing plane and also quite irregular plane when it comes to oxygen.
Okay, and in such a case, what is the real structure of the monoclinic phase? When we take into consideration this arrangement of oxygen in the nearly plane, buckling plane, and the plane which is as literature says, plane quite irregular.
I'm not sure here.
Okay, maybe you remember, if we observe the zirconia grain after the transformation, after the transformation into the monoclinic polymorph, the, let me say, totally whole gray grain, which can be visible in the SEM image, is this grain, which is gray before transformation, is after transformation only smoothly, let me say, gray with no any visible additional features. Could you please comment this image?
Yes, so as we could have seen on the previous slides, you said that transformation from monoclinic to tetragonal takes place in higher temperature than in reversed direction. So I mean, the mechanism of those two transformation is different.
Okay, and what are the features of the T2N transformation, tetragonal to monoclinic? What are the basic features?
Different microstructure or density.
Okay. Okay. Please read this information.
First order phase transformation, diffusionless shear process, athermal.
Yes. Needs overcooling.
Proceeds near sonic velocities, depends on the particular size. In some cases, reversible, causes dramatic damage of a microstructure of dense crystalline pure zirconium oxide. Belongs to the class of martensitic transformation.
Martensitic transformations. Yes, that's right. How do you understand this information? The first order phase transformation. What is the main feature of this transformation? Maybe you know. Maybe somebody knows.
You mean the Gibbs energy? I'm not sure.
Is it the
Yes.
formation of the leftover main phase, the phase before the transition?
Could you please repeat?
Is it that not all of the material is transforming to in the martensitic transformation, and there are leftover material from the previous phase?
Okay, you say about the not fully transformed grain, yes?
Yes, maybe.
Sometimes it happens, but typically not. Okay, but two questions were okay. Okay, the first question for Ms. Claudia Wyszczarz was concerned. What is the view of grain before and after transformation, after the transformation? And the answer is like in this picture. Yes, we observe layers, like a layered structure. Yes, and maybe Claudia knows how to name these layers. Claudia, do you hear me?
Yes, I can hear you, but I can't remember the name of it.
No? Could you please translate this word? Can you see my mouse?
No, I can see.
Okay, I'm sorry. How to do that? Okay, just a moment.
I mean, not to confuse you, but I can see the mouse. So it's
Yeah, I can see it too.
Not your fault. You can see the mouse.
Okay.
I think I just have the microphone button in this space that you had your mouse. So do you mean martensitic twins?
Yes.
Oh, okay. So now everything is clear.
Yes, twins. Okay, twins. Okay, And another question, well, how to understand what are the main feature of the first order phase transformation? Maybe you remember from the physical chemistry?
I think that I can remember that there was something that it wasn't constant. I mean, I don't know how to translate state. Oh, yeah, state. True. So I think that it was not constant change of state, as I can remember from
yes, that's right. But what about the heat transfer, energy transfer? Does it appear or not during the first order transformations? The exchange of heat. Is some energy of in the heat released or absorbed, let me say, due to this transformation or not? The first order transformation.
I think it is possible to.
Yes, that's right. You are right. Okay, and if we take into consideration, you see, maybe okay, just a moment, maybe. Yes. Could you please comment this this slide?
Yes, so we can see.
Does it show the first order transformation? Okay. This is the DSC curve. What does it mean? DSC curve? Differential scanning calorimetry. Heat flow as a function of temperature during the transformation. Yes. The material has been cooled with a rate of 10 degrees per minute. Cooling. Yes, cooling. And each peak must be attributed to what, Claudia?
To the temperatures of different transformations.
Yes, to the transformation. Which one?
Can you repeat the question, because I don't understand now?
What type of transformation is shown here?
Monoclinic phase into tetragonal.
No,
in a different direction, tetragonal to monoclinic phase.
Yes, that's right. DSC curves showing the tetragonal to monoclinic phase transformation on cooling. Yes, and as you can see, because this transformation is the first order transformation, we can measure the heat which has been released when one structure, tetragonal, higher temperature, yes, higher temperature structure transforms into the monoclinic one. And we can measure the, let me say, the energetic effect. And we can compare the temperatures of those effects for different powders that differ in the particle size. And concluding this this picture, this picture, the temperature of transformation is a function of the particle size. The lower particle size, the lower the tetragonal to monoclinic phase transformation. Okay, one feature is the first order transformation. Yes. What else? What else? Okay, just a moment. Miss Claudia, for me, very good.
Thank you.
For me, very good. Okay, and another features, diffusionless and athermal process. How this information is understood, let me say, by who wants to explain me what does it mean diffusionless shear process and athermal process? Who want to start to discuss this problem? What does it mean diffusionless shear process, athermal, needs overcooling? Mr. Marcin Tomkiewicz?
Yes, so diffusionless shear process. Do you mean the twinning? Yes.
I can say yes and not. Because not exactly. Diffusionless.
Yes.
Diffusion means for you what?
The action of moving an atom or particle through somebody to make the concentration equal of that particle.
You said molecules?
Molecules and atoms.
Or atoms, yes. Okay, and diffusionless, it means that
there is no diffusion.
There's no diffusion. Could you indicate for us any mechanism of diffusion in solids? The diffusion mechanism in solids.
For example, I don't know in.
Okay, what are the paths of diffusion of atoms?
For example, then they can switch places in the structure, the cations and anions. No, the places in the crystalline structure to from
which are free, which are empty, yes?
Yes.
And how to call those empty places? And they can be what?
Vacancies.
Yes, that's right, vacancies, for example, or interstitial places, yes. Okay, and there is no diffusion means that what are the distances of movement of atoms during the martensitic transformation, during the tetragonal to monoclinic polymorph transformation? What other distances, in your opinion?
So less than one how do you say it in English?
One atomic distance, yes?
One atomic.
Yes, that's right. Okay, and another question is, and problem, is it possible to overcool the martensitic transformation?
Yes.
You say yes. You said yes. Because you understand, the martensitic transformation needs overcooling to appear, yes? Or
yes.
overheating to appear. Yes. But is it possible to overcool this transformation?
Yes, because you have to have you have to be in some kind of field of the temperatures, because if someone cools it too quickly, the material, the material can not go through martensitic change.
Okay, I think you suggest, answering yes, my question, that is it possible to save the tetragonal phase in the material structure when we cool the material to the room temperature with very high speed, high rate, yes?
Yes.
You suggest that it is possible.
Yes.
But could you please explain us the meaning of the informations? What informations are given by this this graph? The relationship between Helmholtz free energy and the temperature. Could you please describe the informations showing by this this slide for us?
So the Helmholtz free energy is declining in on the where there are two straits, and the parent phase and the martensitic phase, and they meet in the T0 point. So on the left hand side, the Helmholtz energy is more than 0, and the right hand side is less than 0. So that on the Helmholtz free energy is less than 0. The martensitic phase should be is the better one, I think.
Okay, could you explain us a meaning of this note, this symbol, MS?
It's the martensitic start temperature.
Yes.
Yes. And the AS is the temperature for the reverse transformation, and that means that we have to overcool our overheat. And now I see that
Okay. Okay.
probably the question wrong. That you cannot overheat or overcool.
Okay. Yes. Because the temperature, sorry, the transformation will appear at MS independently on the cooling temperature. Yes, we can cool slowly and go to MS. We can cool the material very quickly to MS and then further. But at this temperature, at the Martensite start temperature, the transformation will start each time independently of the cooling rate. Okay, it's not possible to overcool the tetragonal phase. The tetragonal phase, which shows us a lower Helmholtz free energy at the temperatures higher than T0. Yes, we cool this phase, and after reaching and passing the T0 temperature, the tetragonal phase is how to say the state of the tetragonal phase at how to name the state of tetragonal phase at the temperature range from T0 to MS. Is this phase stable?
I think it could be metastable or something.
Yes, it is metastable. Yes, metastable, and the energy goes through this line, and then when MS is reached, delta F is so high that the transformation starts and proceeds with the sound rate, because this is the shear process. Okay, I think now you understand this. Good. What? Okay. I think we understand first order phase transformation, diffusion layers, shear process, athermal. Athermal means that the process does not need the temperature for keeping in let me say movement. The transformation when MS is achieved, this temperature, it goes independently on the temperature. The kinetics of the process do not need the thermal activation. Good. Twins that were formed after the transformation. Sometimes, as one colleague said, the grain can be partially only transformed, but typically twins are formed. Maybe somebody knows why twins are formed. Patrick, Zions?
Yes.
From the thermodynamic point of view, why twins are formed during the transformation, martensitic transformation of tetragonal to monoclinic phase? In your opinion, why they are formed?
because of the shear stress, and when the structure of zirconia is up under stress, it's easier for the lattice and to, I don't know how to call it, to bend or just to twin, apart from different change in structure.
Okay, if I understood correctly, you said that this process minimizes strains of this structure. Yes.
Yes, this is how I imagine this.
Okay. Okay, and another problem. I want to stay with you, Mr. Patrick, and could you please discuss the thermodynamics of the T2M transformations? What are the components, energetical components that control the tetragonal to monoclinic phase transformation?
You mean the different types? Okay.
Yes.
So as you can see, the first is the change of Helmholtz free energy.
There are three components. Could you please describe us how to understand those three components?
No, so the first
what are attributed to what they are attributed.
The first is attributed to the change of specific heat.
Specific what?
Heat.
Specific heat. Okay.
Is it okay?
Is it possible to change this this component for the zirconia systems? How to change? Oh, if it is possible, of course. This component delta FC.
Probably yes, but I'm not sure.
Okay. Okay. Technological.
Maybe via different particle size, or adding a stabilizer.
Okay. I think you have read this this sentence: change of Helmholtz free energy connected to a change of chemical properties of the system. How to change chemical properties of the system?
Via changing the chemical squad, like adding a stabilizer, like for example,
yes,
yttrium oxide.
Yes, for example. Okay, and this is the correct answer. A change of chemical properties means a change of chemical composition, simply chemical composition of the system. Okay, another component, delta FS, sorry.
So this is connected with surface free energy, and this can be changed with a different particle size that we use to process our material, to achieve our material.
Okay. What types of surfaces can exist in the zirconia systems? Very simple questions.
For sure, the grain boundaries.
Yes. Interfaces.
Yes.
Boundaries between different phases.
Yes, and maybe that we're talking still about the powder, or about the
Yes.
material after sintering.
Yes, free surface. Yes, free surfaces. Okay. And is it possible to change? Is it possible to change the structure of zirconia powders by grinding, by milling? Is it possible to change the structure, in your opinion, of zirconia powders simply by grinding?
I mean, you mean the chemical structure or the size of the grain?
The polymorphic type, the crystallographic structure. Atomic structure, atomic arrangement.
Yes, it's possible. It's possible. I mean,
how to do that? How to do that?
Maybe adding, as before, adding the stabilizer.
Okay, imagine that you take monoclinic powder and you start grinding it in let me say very effective mill. And what will happen when the size of monoclinic grains, the size of monoclinic particles is reduced with time?
So the specific surface area are higher and large.
Yes. And what must happen at any size of particles, monoclinic particles, and why?
Could you please repeat?
What we must expect to happen? What we must expect to happen when the size of particles is reduced to the some value.
Agglomeration of this very small particles.
Okay. How to understand this information? The surface energy of the tetragonal phase is less than monoclinic. Yes, during milling, the size of monoclinic particles is reduced. And it means that the surface of the monoclinic phase increases.
Yes.
And the energy, of the system also increases. Let me say this: the Helmholtz-free energy, the Gibbs-free energy increases. But is it possible any mechanism which will decrease the energy of the system which is under milling?
So maybe change into the tetragonal phase.
Yes, that's right. Yes. Spontaneous monoclinic to tetragonal. What is the character of this transformation? Athermal or thermal activated? Martensitic or non-martensitic, in your opinion?
I mean, I think it's martensitic.
Yes, it is reverse martensitic transformation from monoclinic to tetragonal due to only the size of particles. Okay, and the and the last component of this equation, but maybe somebody will continue. Thank you very much, Mr. Patrick, for a very good answer. Who wants to describe the third component of the Helmholtz free energy of transformation, tetragonal to the monoclinic? Miss Agnieszka Majecka.
Yes, I'm here.
Could you please give us some comments concerning this component, delta Fe?
Change of energy of elastic deformation, but I don't know what else could I say.
Elastic deformation, yes, that's right. To what we must describe this component? The change of energy of elastic deformation. What are the sources of this component? What are the sources of the change of energy of elastic deformation in the zirconia containing systems? Okay, one thing, is there any elastic deformation generated during the transformation of the tetragonal particle, tetragonal grain into the monoclinic one?
Could you repeat your question? I'm sorry, because
Yes.
something is wrong with my connection.
Is there any energy of elastic deformation generated first during the transformation of tetragonal particle to its monoclinic counterparts?
To be honest, I don't know.
Okay, and please take into consideration the change in density, maybe specific volume of tetragonal and monoclinic structures during the transformation. Is there any change in the specific volume which accompanies the transformation?
I don't know.
Okay. What I can say?
I can understand
I
your
must
question.
ask Miss Małgorzata Mendela. Sorry, Mendela chyba. Yes?
Okay, but can you repeat your question?
Generally, I want to get answer on the question, what are the sources of the energy,
elastic
the
deformation.
change of the energy of elastic deformation, but I asked also, is there transformation accompanied simply by the change in energy of elastic deformation?
Okay, so source of that elastic deformation can be some inclusions in zirconium dioxide.
How to explain this? You said simply
Inclusions.
inclusions. Okay, I think you all understand that the elastic deformation energy accompanies the deformation of the structure, which appears during the process, some processes. The elastic deformation, which appears during the transformation, and energy accompanies this process. Yes, the structure changes its volume, and to do that, some work must be done. And what are the sources? Okay, change of energy of elastic deformation connected with the transformation and external stresses. How to understand this? Transformation and external stresses. When the polymorphs of zirconia were characterized, I don't remember who, but your colleague said that during the tetragonal to monoclinic transformation, the increase in the volume of monoclinic phase appears. Yes, and do you remember what is the value of this volume increase? Which accompanies transformation. Sorry?
Unfortunately, I don't remember. I think you mean the structure changes, yeah?
Yes.
And
tetragonal to monoclinic.
Okay.
Density changes also, yes. The density decreases or increases before transformation tetragonal phase, after transformation monoclinic one. And the specific volume of tetragonal is...
tetragonal is density is higher than the monoclinic.
Yes.
And the change is about, I don't remember, 4% less, but I don't remember
4 or 5%.
the exact number. Yeah.
Yes, 4 or 5%. This is the change in volume. The grain, which transformed into the monoclinic phase, forming twins, always changes its volume by 4 or 5%. And is this the source of deformation? The deformation of the structure? I mean, if you imagine the grain which is embedded with other grains, embedded with the polycrystalline material. Yes, it means that grain transforms, and surrounding grains, I think, feel this transformation. Is there any deformation in the surrounding grains or not?
I think yes, there is.
Yes, should be, yes. And this is the source of the energy of elastic deformation, one source. But what about the source which is called as external stresses? External stresses. How to understand this?
Maybe it can be, but I don't know if I'm right, some pressure to the grains? Sorry? Pressure to the grains, or external, but I don't know.
Okay. Okay. If we have a composite of zirconia and alumina, a mixture of zirconia and alumina grains in the polycrystalline material, are the thermal expansion of those two phases the same or not? Those two materials, alumina from one side and zirconia another side, and the thermal expansion coefficients, they are the same or not? Thermal expansion coefficients for zirconia and for aluminum oxide.
I don't know, I'm sorry.
Are they the same or not? But what do you expect typically? Is the typical situation for different phases of different structure composed of different atoms of different chemical composition? Is the typical situation to show the same thermal expansion coefficients? I think not. Maybe you know what are the results of the thermal expansion coefficient mismatch when thermal expansion coefficients are not the same for different phases, when they are when the material was produced from powders. The powders were sintered at high temperatures, and after sintering, the material is cooled down to the room temperature. And if the phases have different thermal expansion coefficients, what are the final state of stresses, let me say, in the material? Is the material free of stresses?
Yeah, I think that no, there are stresses in the material.
There are stresses, yes. And those stresses are the external stresses for the T2M transformation. Zirconia grain in the other material matrix, zirconia grain is always in the state of stresses, thermal stresses coming from the thermal expansion coefficient mismatch. Okay, thank you very much for your time for this meeting, and we will meet after Easter's, and happy Easter's for you.
Thank you, but could you tell us when can we expect that you will add topics for next seminar?
For the next seminar, okay. Let me say let me see calendar. We have okay, lectures. The lecture is okay, only one lecture. No, two lectures. Tomorrow, the first, not tomorrow, 24th and 30th. I think that after the fifth lecture, simply.
Okay, because this time we also didn't have the lecture, and it was hard to us to prepare for this seminar.
Yes, I know. Okay, in such a case, I will give you topics for the lecture 4th, which will which will be given for you 24th March. Yes, the first part, and after the next lecture, I will give you the last part, the second part of questions. Okay.
Okay, thank you.
It will be area. It will be area. It will be area. Just after the lecture on 31st March, I will give you the topics, but the first part will be given earlier.
Okay, thank you.
Yes, of course. Oh, wow. Yes, answers for the questions. It needs time from me, which I have no time. But I don't know how to solve this problem of answering and answers and comments that are during this our seminars. I don't know how to solve this problem, because I can deliver you only the notes from my lecture and only the literature I used and selected for this these lectures, and this is only way. I don't know. If you want, you can record seminars. For me, it's not problem.
I think what Marceli was asking about.
If you agree for recording, I can do this.
Yeah, technically it's
great.
We can
great.
speak Polish now. I think
great. Wow. Yes, of course. Yes, of course. Okay. For today, my grades for your participation in the discussion: Marceli Hryniewiecki 5, Klaudia Łuszczarz 5. Sylwia Manteris 3.5, Małgorzata Mendela only 2, Miss Agnieszka only 2, Miss Artur Polaczek 3, and Patrick Marcin and Patrick 5 each man. But those grades are let me say they are influenced greatly by the fact that you received the topics today, and I will not take into consideration those grades for Miss Małgorzata i Agnieszka for the for what for final grade. Okay.
Excuse me, can you read the notes, the grades from the previous seminars?
From previous seminars? Oh, I have got you only pluses. Plus.
Okay.
It means that the positive voice in the discussion, I only noted. Good. Happy Easter in such a case, and see you. No, happy Easter's from seminar only, but we will meet. We will meet in into lectures, our lectures. Okay, and I must say goodbye and see you next lecture.
Well, thank you.
Goodbye.
Goodbye.
Bye. Thank you very much and goodbye.